Okay, hello everyone. My name is Ravi Prakash Singh, and today I will talk about DBSCAN. So our objective here is to learn how DBSCAN clustering work and why we should learn it, and how to implement DBSCAN clustering in Python. So in introduction part, I would say that clustering is a process of partitioning a set of data in a meaningful subclass called cluster. So in cluster, we have a collection of similar objects. And DBSCAN is one of the unsupervised clustering algorithm. Now coming to the things we will cover in this uh, is we will talk about why do we need DBSCAN and what exactly it is. We will talk about some terms of it like what is reachability and connectivity, and then we will talk about the parameters on which we can tune our DBSCAN, and we will talk about the parameter selection way also. So after this, we will see the algorithm set step by step, and since we are talking about algorithm, then we will see that time complexity of this algorithm as well. And finally, we will be implementing our DBSCAN clustering in Python. Now, coming to the first topic, which is why do we need DBSCAN? So, actually, clustering is an unsupervised learning technique where we try to group data points based on specific characteristics. So there are various type of clustering algorithm like k-means are the hierarchical, and these are the most used clustering algorithms. So the basic question is, if we already have basic clustering algorithm, so why do we need uh, a new clustering algorithm and spend time and energy on learning it? So yes, it is a very obvious question, but there are some problem, and like the k-mean and the hierarchical clustering both fails in creating clusters of arbitrary shapes. They are not able to form clusters based on varying densities. So that's why we need DBSCAN clustering. And DBSCAN is not just able to cluster the data points correctly, but also it perfectly detects the noise in the database, and it gives some notation to that noise as well. So we will see the difference in the clustering of k-mean and the hierarchical clustering and the DBSCAN when we'll be dealing with our Python program execution part. So going to the next part, which is what exactly is DBSCAN clustering. So actually, DBSCAN stand for density-based spatial clustering of application with noise. So DBSCAN is a density-based clustering algorithm that works on the assumption that clusters are dense region in the space separated by regions of lower density. Means a dense region, and if there is a region with lower density, then the dense region will be a cluster, and the lower density region will be a margin type of the thing or the divider type of the thing. So it groups the densely grouped data into a single cluster, and if it can actually identify clusters in large spatial data set by looking at the local density of that data point. The most exciting feature of DBSCAN clustering is that it is robust to the outliers. So it also does not require the number of clusters to be told beforehand. Means we are not required to tell that our data is going to have this much number of uh, clusters or the group. Means it will figure out on its own that there are this number of clusters. But when we are talking about k-mean or the other clustering algorithm, then most of them requires to know the number of centroids. That is basically the number of clusters which may be found in our data. So this is a good thing for DBSCAN, and DBSCAN requires only two parameter, epsilon and the minimum point. So we have to understand what is this epsilon and minimum point. So epsilon is the radius of the circle which we will create around each data point to check the density, and minimum point is the minimum number of data points required inside that circle for that data point to be called as a core point. So yes, we have to define this core point as well, so means the importance of this core point. So we'll do it in the next slide. So now talking about this we are talking about this circle type of things. So this circle type of things comes because uh, till now we are talking about data having two features, means two-dimensional data. So if we are having some higher dimensions, means our data is having more than two or three, four features, then that will be higher dimension. So in higher dimension, the circle become hypersphere, and this epsilon become the radius of that hypersphere. So uh, yes, and this minimum point is the minimum number of the data points required to be inside that hypersphere for that point to be called as a core point. Now going next. So DBSCAN creates a circle of epsilon radius around every data point and classifies them into core point, border point, or noise. So we have to understand what are these three different types of points. So first, talking about the core point, a data point is a core point if circle around it contains at least minimum number of, means mean point number of points. So if min point is 2, then there should be at least 2 points in a circle of epsilon for a point to be a core point. And if the number of point is less than the number of min points, then it is classified as border point. And if there are no other data point around any data point within the epsilon radius, then it is treated as noise. So here this figure is for a DB scan with minimum point equals 3. So now if we look for any of these red points, let's say we take this red point. So for this red point, we have 1, 2, and 3. 3 points in this epsilon radius. So this is a core point. Now coming to this, we have 1, 2, 3. Also, again, this is also a core point. So all these red points are having at least 3 points in its epsilon radius. So all these red points are the core point. Now coming to this yellow points, we are having 1 and 2. Just 2 number of points in this epsilon radius, which is less than the number of points required to be a core point. So this is a border point. Same is for this yellow point also, because we are having 1 and 2, just 2 points in this epsilon radius. Now coming to this purple point. So here we are having just 1 point and no other point in this epsilon radius. Similar is the case here. So these 2 purple points are the noise point. Now going next. One more thing which is very important here is that actually, since we can have multi-dimensional type of the things or different type of things, so it is not mandatory for us to talk about this distances to be an Euclidean distance, because for locating data point in space, DBSCAN uses Euclidean distance most of the time, although other methods can also be used, like great circle distance for geographical data. So it can also need to scan through the entire data set once, whereas in other algorithm we have to do it multiple times. So we can define distance, means the thing which we are talking here, calling is here distance, can be something other, means the Euclidean distance will be coordinate of this and coordinate of this. So if this is x1 x2 and this is y1 y2, so it will be x1 square minus y1 square plus x2 square minus y2 square under root. So that will be the Euclidean distance, but we can have here some distance like under root x minus y plus y minus plus x2 minus y2 kind of thing. So this is now going to the next slide. So here we are having some terms like reachability and connectivity. So these are the two concepts that we need to understand before moving further. So talking about the reachability state. So if a data point can be accessed from any other data point directly or indirectly, then it is called a reachable state. And connectivity state is whether two data points belong to the same cluster or not. So in terms of reachability and connectivity, 2 points in DBSCAN can be referred to as directly density reachable, or density connected. So let's understand what they are. So when we talk about directly density reachable, so uh, let a point X is directly density reachable for from point Y. So for fixed epsilon and the minimum point thing. So for that, what should happen, that X belongs to the neighborhood of Y, that is the distance of X and Y is less than epsilon, and Y is a core point. So here we can see that Y is a core point, and this X is next to Y because we can clearly see it here. And the distance between X and Y is less than this epsilon. So this is very clear that this X and Y are directly density reachable. Now coming to the next type. So here we have density reachable. So a point X is density reachable from point Y for fixed epsilon and minimum point if there is a chain of point P1, P2, P3 up to Pn and Pi, where P1 is X and Pn is Y, such that Pi plus 1 is directly density reachable from Pi. So we have to check the relationship between this X, means the connectivity between this X and Y, this X and this Y. So for that, we will check first the connectivity between these intermediate steps. So this X is connected to P2 being directly density reachable, and this P3 is directly density reachable to P2, and this P3 is directly density reachable to this Y. So using the above definition, we can say that this Y is directly is density reachable to X. Now talking about the density connected. So a point is density connected from point Y for fixed epsilon and minimum point if there exists a point O such that both X and Y are density reachable from O for again the fixed epsilon and number of minimum points required. So we have to check the connectivity between this Y and X. So this X is directly density connected to this B, and this B is also directly density connected to this O. So we can say that O and X are density reachable. Similarly, O and Y are also density reachable because this A and Y are directly density reachable, and this A and O is also directly density reachable. So we can say that this Y and O are density reachable. So using the above definition, we can conclude that this Y and X are density connected. Now moving to the next slide. So here we will talk about the parameter selection in DBSCAN clustering. So basically DBSCAN is very sensitive to the values of epsilon and minimum point because these are the only two parameters on which it depends. So we have to very thoughtful before selecting our epsilon value and the minimum point. So one very basic thing is for minimum point is that it should be greater than the dimensions of the data, means the number of features in our data. So we can say that minimum point is always greater than or equal to dimensions plus 1, and it is a good thing to have. And now the next thing is selection of epsilon. So the value of epsilon can be decided from the k distance graph. The point of maximum curvature forms an elbow in this graph, and if there is an elbow, then that tells us the value of our epsilon. So we will see it in our Python execution code. Now talking about the DBSCAN algorithm. So there are 4 steps here. Basically, there are 3 steps, and this fourth one is just calling these steps again and again. So in first step, we decide the value of parameter epsilon and minimum point, and this is actually a very important step here. So for each step, in the next step, what we will do that for each data point present in the data set, we will compute its distance from the other point. And if the distance is less than or equal to the value of epsilon fixed during the step 1, then we will consider that point as to be a neighbor point of x. And if the data point x gets the count of its neighbor greater than or equal to minimum point, which again is fixed during the first step, then we will mark it as to be a core point. Or and again, if we mark it a core point, then it will be a visited point as well. So in step 3, for each core point, if it is not already assigned to a cluster, then we will create a cluster, means create a new cluster. And further, all the neighboring points are recursively determined and assigned the same cluster as that of the core point. And now we will repeat the above steps until all the points are visited. So these are very simple 4-step algorithm, DBSCAN, and we will execute it in our Python code. Now talking about the complexity. So since we know the algorithm here, so the time complexity, basically the time complexity is mostly governed by the number of region query invocations. DBSCAN executes exactly one such query for each point, and if an indexing structure is used that execute a neighborhood query in log n time, then an overall average runtime complexity of n log n can be observed in DBSCAN. In this case, what I actually mean to say that the parameter epsilon is chosen in a meaningful way, that is such that an average only log n points are returned. And if we are not using an accelerating index system or degenerated data, uh, then in that case, all points within the distance less than epsilon, the worst case runtime complexity will come out, and it will be order of n square. So now the next part is implementing DBSCAN clustering in Python, and we will do it in Jupyter Notebook. So now I'm going to do the Python implementation of this DBSCAN. So here we will need some direct Python libraries. So I've taken NumPy, Pandas, Matplotlib, and Math. So I have to run this first cell. Now we need to create a database, some data over which we can apply our this clustering algorithm. So I've decided to make a 2 feature data, which will be very easy to visualize here. So for creating this data, I have created a function that is I named it as point in circle. So I have to give this 2 values. One will be r and the radius, and other will be the number of points I want to be in that circle. So it is just directly based on cos and sine curves. So we will get some circle out of it. So I fixed this to be directly 200 points will be there in a one circle. So and all these points are randomly generated, but it is generated only in that circular ring type of area. So going next, I have run it, and so now if I'm going to use just one circle and try to do some clustering work over here, then it will be kind of meaningless. So I'm what I'm going to do is I'm making some concentric circles. So I'm recalling this function 3 times and making 3 concentric circles here. So these concentric circles are of different radius and different number of points in them. So that's all. Then I plot them in our next cell. So the plot of the data set looks like this, and I've labeled it this to be a feature set 2, and this is feature 1. It's a basically a 2D data. So now if I try to run and apply k-mean algorithm over it, so we have to give two values to it again. So this will be the number of clusters, which I've already told in my previous part, and we have to give it some random state. So I just called this k-mean function from our sklearn library, and now I'm going to plot this. So the plot look like this. So we have given it 4 clusters. So here we are getting uh, one red color cluster, one purple color, and one blue color cluster. So if I add here a green color cluster as well, then green color cluster. So yes, we are getting here some 4 different type of clusters, and this is how the k-mean clustering work. Now if I give it some 3 cluster type, then it will plot like this. So actually it is not recognizing the shape here, because uh, since I'm giving 3 concentric circles, so this is basically the problem of k-mean, because which I told during the intro of DBSCAN. So it is just making cluster on its own, because there is no sense of these points being in this cluster and these points in being this cluster, because these two are very close to each other, and the separation is actually in the concentric rings here, but it is dividing in on its own. Now coming to the hierarchical clustering, so I've again taken it from scikit-learn, and here if I give cluster value to be 5, then the graph looks like something this. Here also, the shape is not density based, means it is not clustering it on the basis of density, it is clustering on the shape it takes from its own algorithm. So yeah, this is the problem which we get from these two. So if we want some density based clustering, so we have to go and use DBSCAN. Now I'm going to do DBSCAN. So again, I have called it from the scikit-learn, and but here I've not given any parameter value. Means I have not given some value to the epsilon thing or the mean point. If I run it like this only, then it is going to show means it is going to say that all points are points in a one cluster, or we can say that all points are not as anything. So but now we need to know the value of our parameters to have a good clustering. So let's say so actually the minimum point which I talked about, so it will be, it should be always greater than or equal to or equal to number of dimensions plus 1. So here we are having 2 dimensions, so we will set it something 3, 4, or 5. And now we have to we have to set search for the epsilon value. So we will do the thing which we talked earlier, that we will see the plot of k distance graph. So I call the function which is nearest neighbor. So we will use it to plot our k distance graph. So when we plot our k distance graph, basically this k distance graph is just the distance of each points from a, means we will first choose a point and then we will plot the distance of that one point from each points in the graph. So if the first neighbor is at this distance, second is at this distance, so it depends on that thing only. So we see that after some 25-30, we are going to get a very sharp raise in this distance. So this will be our epsilon value because we are getting a NISER here. So now if I feed this epsilon value to our DBSCAN, so let's say I give it to be 30 and I set my minimum sample to be 4, that is obviously greater than number of dimension plus 1, that is greater than 4, greater than 3, sorry. So now I run this code and I go and see the plot. So here we are getting different clusters. So this is the first cluster, this is another cluster, and this is another cluster. And to this red points, it is marking as to be a noise. Now, if I change this, let's say I give this epsilon value to be 25. So the noise thing is this green, and here we are getting just 3 clusters, and now it is not getting that shape, means it is not getting that precise shape which we want. So we can change it again. Now let's say if I change this to 35, so here we are getting that these 3 are the different clusters and this green one are the noise. And now if I change this sample to 5, again we get that these are the 3 different clusters and this green one. So this is very good, and DBSCAN is amazing cluster the data point into 3 clusters, and it also detects the noise in the data set represented by the green color here. So one thing important to note here is that though DBSCAN creates cluster based on varying density, it is struggles with the cluster of similar densities. Also, as the dimension of the data increases, it will be very difficult for us to execute DBSCAN to create clusters.